Hello, everyone. I'm glad to share our work with you today. The title of our paper at ECCV is Rate-Distortion-Cognition Controllable Versatile Neural Image Compression. First, let me briefly introduce the image compression. The goal of image compression is to compress images into high compression rate binary bit streams while maintaining high fidelity. However, previous image compression methods have typically been optimized for human visual perception or fidelity, mainly aiming to improve metrics like PSNR and MSSSIM. This results in suboptimal performance for some downstream tasks, such as object detection and classification. For example, when performing object detection, the primary focus is on the objects within the image. Allocating too much bitrate to maintain the background's fidelity does not enhance detection performance and leads to wasted bitrate. Moreover, for different bitrates, downstream tasks, and trade-offs between image distortion and task performance. Different image compression network parameters are usually required, which poses a significant challenge in terms of training and storage resources. Therefore, we aim to propose an image compression method that can control the rate-distortion-cognition performance within a single network. The framework of our method is shown in the figure, which is mainly divided into three parts: the primary branch, the auxiliary branch, and the rate-distortion-cognition trade-off. The primary branch is used to train a cognition-oriented variable bitrate codec to improve the performance of multiple downstream tasks. The auxiliary branch reduces image distortion by transmitting additional bit stream. Finally, we use an interpolation method to achieve the distortion-cognition trade-off. Next, we will introduce our method in more detail, based on these three parts. First is the primary branch. Previous works have suggested that using semantic level loss to optimize the network can improve image performance in downstream tasks. Therefore, we adopt a contrastive loss to optimize the network, derived from MoCo. To mitigate the impact of outliers in the reconstructed images, i.e., pixels greater than 1 or less than 0, we employ a local MSE loss to constrain these values, ensuring the final output falls within the 0 to 1 range. The final loss is a combination of the bitrate loss, contrastive loss, and local mean squared error loss. To achieve the rate cognition trade-off, we introduce gain units to control the precision and loss for different channels. Specifically, we set several learnable parameters to control the channels, multiplying them before and after the quantization of the latent code Y, enabling us to control the loss generated during quantization. Furthermore, we introduce an auxiliary branch that uses a small amount of bit stream to supplement details and reduce distortion. This branch is optimized using MSE loss. Through these operations, we achieve both the rate cognition trade-off and performance optimization for multiple downstream tasks. Additionally, we employ an interpolation method to achieve the distortion cognition trade-off. Specifically, we combine the outputs of the primary branch and auxiliary branch with a weighted factor, beta. By adjusting the beta value, we can control the trade-off. When beta is close to 1, the cognition performance is stronger, and when beta is closer to 0, the distortion is lower. Here we show our experimental results. The blue area illustrates the range that can be regulated by our single model. The labels A, B, C, and D in the top and bottom diagrams correspond to each other. As you can see, we achieved superior performance in classification, segmentation, and detection tasks compared to other methods. We also achieved controllability for the rate distortion cognition trade-off. For example, at point A, we achieve the best cognition performance, but with higher distortion. At point B, the distortion is minimal, but the cognition performance is relatively poor. Thank you for your attention.